In this video, we're going to start a series of video about substitution reactions at aromatic compounds. And so first, we're going to be talking about the three, main mechanism type of reactions, because studying those is important to be able to solve problems and predict products in plant synthesis as well. So first, in aromatic substitution, we have three essential type of mechanism. The first one is electrophilic aromatic substitution. We're going to talk about that in a minute. The second mechanism we call is substitution, but by nucleophiles, and so we call that SnAr, so aromatic system. And the third mechanism is elimination, addition, and this goes through a benzene intermediate. So I'm going to have benzene intermediate. So three different mechanisms. It's important to know how that works, because we are going to be needing to predict products. So first, in electrophilic aromatic substitution, what we're looking at is, say, some aromatic system. Let's put just benzene. The reaction is going to happen with some electrophile. And in that mechanism, you're going to have the nucleophilic attack, say, by pi electrons in the ring over to the electrophile. And that is forming now the following intermediate. I have the electrophile. Here is an H. Here you have 6 H's, one on each carbon. Now you're going to have a positive charge here and here, and that's step one. Say step one. Again, nucleophile is the pi electrons in the ring. That's your electrophile. This is an intermediate that we call the sigma complex. And what we're doing in this is now we're going to draw the resonance structures of that intermediate. So we know that we can do this. And in doing so, putting my double bond there, here you still have H, E, and I can continue moving electrons. And I'm going to have now the charge here, double bond, this is H and E. So all of that represent the resonance structure of the sigma complex. In another step, second step, then we're going to have some base, and that depends on what are we using as electrophile, what is the condition. But again, say that I have a base. In the second step, the base is going to remove the hydrogen, and we're going to restore aromaticity. And at that time, then we will have the substitution on the aromatic ring. So reactant product, that's my intermediate. In general, that goes through the following profile. That's my product, that reactant. Here I'm going to have my intermediate, and I'm going to draw just sigma. Say this is potential energy. Going that way, this is reaction coordinate. It is important that to understand that the nucleophile is a ring, because rates of reaction depends on what is in this ring. So when we have different substituents in the ring, say that we already have something like this, and this is anisole, this will behave different as if we have, for example, a chlorine. In the sense that if any of these react with an electrophile and you have another substitution, things are going to be different in regards to reaction rates, and that we call activated system or deactivated, and also predicting products. So it is important, again, recall that the nucleophile is pi electrons here, and we have an electrophile. So that's my first type of mechanism, and this is about electrophilic aromatic substitution. The majority of the reactions that we're going to be seeing in this chapter when you do reaction are electrophilic aromatic substitution. But still we have a few reactions that happen through substitution by a nucleophile. Now let's look at what we need, in that case, requirements, say, for that reaction to happen. So here we have that, and I'm gonna, in the case of the electrophilic aromatic substitution, here you need an electrophile. And the nucleophile is actually 5 electrons in the ring. Okay, now this is different. Here, we're going to need this nature of the substrate. We need a few things. Since this is a nucleophilic reaction, we need a nucleophile. It's going to happen by nucleophilic attack, the reagent. Here, the reagent is an electrophile. Now, we need a good leaving group at the ring, and we also need an electron withdrawing group. That was the W. And the electron withdrawing group should be, again, another ortho or para to the leaving group. So as it is right here. And so the way things happen is exactly the opposite of that. Now the nucleophile is going to attack at the ring, and the attack happens at the carbon that has the leaving group. And this reaction is not like the SN2 reaction, but it happens at that carbon. Remember that SN2 reactions happen at sp3 carbon. This is carbon at the aromatic ring. So let's do this. Well, I'm going to draw a specific example. Say that my electron withdrawing group, I'm going to draw an excellent one, and that is the nitro group. And say that I have here a good leaving group. I'm going to add bromide. And I'm going to do that reaction. Say that my nucleophile is hydroxide. So the first step will involve then the nucleophilic attack, and that is at the site where you have the leaving group. And then you move your electrons over, and here you will have a pair of electrons, and here bromide and my nucleophile. But you can other nucleophiles can also be possible. But here you have the other bond still here. And what is interesting, why do we need an electron withdrawing group? Why is that a requirement? Notice that the intermediate here has a negative charge. So that is stabilized by resonance if we have here, for example, the nitro group. If you did this and do the resonance structures here, let's do the first here, I mean a formal charge plus a negative here. And now double bond, and here I have OH, which was my nucleophile, my leaving group. Now you can also take these electrons over here, and you have a structure, a resonance structure, in which you will have the charge, negative charge on the 2 oxygen atoms. So that intermediate is stabilized that way. So electron withdrawing group then favor this reaction. You're going to have the negative charge, notice, ortho to the leaving group. That's my leaving group. So ortho, and you can also have it here. So if you move, you can do another movement of electrons. Instead of going towards the nitro group, you can do this and place the negative charge on the other carbon, ortho carbon. So you will have another resonance structure in which you will have electrons here. So now Again, we see it's similar to the sigma complex that we have here in the electrophilic aromatic substitution. Similar in the sense that it's not aromatic in the intermediate, even though it has conjugation, but it's not completely aromatic. But it's different in the sense that this intermediate, which is called the Meisenheimer complex, is different to the sigma complex, because here in the sigma complex, you had a net positive charge. Here you have a negative charge. So that is what's different. But again, it's not as stable, so higher in energy, that intermediate. And later on, in a second step, you will have the loss of a leaving group. So let's do this. And when you have the loss of a leaving group, your final product that you have here, OH, is again aromatic, and NO2. And you have produced that substitution. So things to remember here, that nucleophile is the reagent. You're attacking at the carbon that has the leaving group. And you must have a good electron withdrawing group, and that electron withdrawing group needs to be ortho or para to the leaving group. So paying attention to that location. If it's not that way, if it is meta, then the reaction will not proceed. So that's the main difference between these two. We're going to be discussing another mechanism yet that is possible, that is elimination addition. But again, majority of reactions that you're going to be seeing in this chapter is predicting products with electrophilic aromatic substitution. Some of them here, and fewer with the elimination addition reaction. And so for the last type of reaction, and I erase what we needed. So here, my reagent is a nucleophile, and I need a leaving group, and I need an electron withdrawing group, ortho or para to the leaving group. Here, the reaction is different, but we're going to explain that in another video. That's for now. Learning how to distinguish these two will allow us to predict products.